Franklin, who's going to be talking to us about cosmology and cross-correlations with ACT and ESO.
Thanks. Great. So yeah, I'm delighted to talk about how we're going to use CMB to be doing cosmology, and in particular how to combine and cross-correlate it with optical surveys. And I'm going to be talking about these two projects in Chile that have these wide field surveys, and that is ACT, that's here, which is finished, but there's now data to be used, and ESO, the Simons Observatory, which is on the far right, that is new and is starting now and is starting to get data and will be the survey of the coming decade. So I'll kind of talk about them both in parallel as these successive projects. Okay, so let me just mention that there are great teams. So the Atacama Cosmology Telescope has been about 160 collaborators. We've been running for 15 years, funded by the NSF, but have now finished and put out our last major data release. The Simons Observatory collaboration is larger. It includes most of those previous people plus many more, and we're more like 400 people or so. And we've had significant investment from the Simons Foundation, and also more recently from the NSF and UK funding agencies and other support too. So let me show you a little movie of the site that we're working on in Chile. It's just near the Alma Plateau up in the Atacama Desert. And so this is a little movie showing, a few years ago, showing the site of ACT. So this is this plateau with ACT pictured there, here. So we're flying over it. It's this 6-meter aluminium dish. Now we're seeing it from above. And it's a millimeter telescope with this high resolution. The 6-meter dish gives it arc-minute resolution. And you see here, it's primary and secondary, and aluminium because it's millimeter wave. And that's focusing the light in this camera here that's now being taken out in this little movie. And that camera was full of detectors tuned to measure millimeter light. So that's the telescope. And you want to be up in a really high and dry place to make these wavelength observations. And so Chile and also the South Pole are the ideal locations for that. So that movie was taken a few years ago, and now what's in place is this new observatory, the Simons Observatory. So here is where that ACT telescope was that we were flying over before. Same volcano is here, and this plateau that was previously just empty is now covered in new telescopes. So we have the kind of replacement for ACT, in a sense, which is this new 6-meter telescope we call the Large Aperture Telescope, pictured here, which has the same resolution but greater sensitivity because its focal plane is this big across rather than about this big across. So you can just pack way more detectors in and increase your sensitivity. Up here are the first 3 of what we call the small aperture telescopes that are really focused on gravitational wave detection from the early universe, a little like the sort of sister experiments at the South Pole. I'm not going to talk about those today because they're not the things we use for cross-correlating with large-scale structure. This is the one that we'll use for that. Okay, so where are we looking? Where did we look? Where will we look? So here we're seeing the sky in equatorial coordinates. Here's the galaxy. And this yellow footprint is where we did observe with ACT. And you'll see we missed out those bits over there. But we had excellent overlap with many of the optical surveys that you see pictured here, pictured down below. Many of you recognize these footprints. We'll be doing the same and more with ESO. So here's the footprint for the ESO, Simons Observatory LAT survey. LAT stands for Large Aperture Telescope. It's the big one. It's the big 6-meter telescope. And here's the coverage we expect. And I realized that my immediate homework is we need to go and put the Roman footprint on here. So that's clear to me. This is very useful. But I believe, right, that it's there, right, for the cosmology survey. And so that's fantastic overlap with these data. And let me just mention the kind of evolution of the field. We talk a lot in CMB about the noise per pixel that we get. If you're doing a half-sky survey at arc-minute resolution, then the thing that tells you how well you can do science is what your noise on a pixel is. That's how we make a map. And so we talk a lot about microkelvin per arc minute pixel. That's the thing we carry around a lot, is what's your sensitivity. The lower that is, the better your map of the sky is. With ACT, we hit a median of 10 microkelvin arc minute sensitivity, which is already a few times lower than Planck had achieved before, which was the previous, previous big satellite. With the first incarnate, with what we've got on sky now, with SO nominal, we call it, the forecast with a few years of observations would take us down a factor 2 lower, 4 to 6 microkelvin arc minute. And then with new detectors that the NSF have been supporting us to put into the same telescope, we should reach down to between 2 and 4 microkelvin arc minute. So a really significant improvement. And I'll just put that in context of where the target has been for the future sort of CMBS4 experiments, which was 1 microkelvin arc minute. So you really see that we're kind of getting down. We're pushing what we're getting on sky now is pushing down towards where the field was hoping to be. Okay, let me show you what the sky we've seen with ACT and what we can expect with SO looks like. I'm showing you a little movie here. You're seeing the Planck sky really here, but only on the footprint that we saw with ACT. So there's this big missing piece that we'll fill in with SO. And we're going to zoom in. And what you'll see is that we zoom in from larger scales into these really high resolution bit of the sky here. This is now the zoom in, where you're basically adding this resolution with ACT that you just couldn't see with Planck. I will just mention that going forward, the CMB field, for now at least, while we have ground-based data, will use Planck at large scales, and we'll supplement it with our ground-based data at small scales. You should think of that as that's the CMB. We'll still be using Planck for years until we have like a satellite that can replace that, because you can't measure the large scales well from the ground. But that's fine, because Planck has done it already, so that's good, in intensity at least. But what we see with this higher resolution is the fluctuations in the CMB. These are the hot and cold spots of the CMB, tracing the density of the early universe, come into finer resolution. And then these spots show up. And you can see them even more clearly in a new way of looking at this image that our colleague Sigurd Ness put together, which I really like, which is an RGB compilation of 3 different wavelengths seen by the millimeter sky. You combine them such that a black body comes out gray. And anything that's not a black body, which is not the primary CMB, shows up in color. And so what you're seeing here is the gray are the CMB fluctuations. But in the orange, you're seeing AGN, radio-dominated AGN. Here, you're seeing nearby dusty galaxies. And here, in the navy blue, here, you're seeing galaxy clusters that are showing up via the Synergies effect that distorts the spectrum. And so I love it. We have actually a web atlas that's linked on our data websites, where you can just zoom around and zoom in and out and change your color scale, go from gray to the old CMB colors. I can spend hours I have spent zooming around it. I encourage you to too. Okay, so this will just get better with SO. Okay, so let's think about the role CMB plays in combining with optical data. I'd say the first role is it's a measurement of the primary CMB gives us a view of the early universe that can then be combined with other data. And so where we are now is this is the measurement of the angular power spectrum of the fluctuations in the intensity of the CMB as a function of increasing multipole and decreasing small angular scales. And you see the beautiful measurement that's already been made by Planck that follows this gray curve, which is the lambda CDM model. And with ACT, we agree, on all of these acoustic peaks and then extend it out to smaller scales. And recent results from the South Pole Telescope are very consistent with this, and they're deeper, as they push out to these smaller scales even better. in polarization, that's really the frontier of CMB. We've improved polarization measurements a whole bunch, and SO will do it even better. Polarization gives you a map of the velocity perturbations at recombination. So think of the CMB intensity as primarily the density of the plasma at redshift of 1100. The polarization of the CMB is a tracer of the motion of the plasma at that same time. And so it gives you a second view of the physical conditions there. And so here is where the advances are even greater, that this is, again, Planck. This is a little snapshot of part of that image of polarization. This is specifically E-mode divergence-like polarization. Planck had already measured this angular power spectrum pretty well, but with ACT, we see it ever clearer. So again, we sort of agree here, and then we start measuring with tinier and tinier error bars out to here. This is pretty cool. This is papers just out a few months ago, and we found that these data points are perfectly consistent with lambda CDM, and one can constrain that model ever better by having this new information. I'll just show you over here an example of how, if you measuring, for example, the baryon density and the spectral index of primordial fluctuations, sort of the Planck data has a different degeneracy than the ACT data, and they combine together to give you a tighter constraint. And I'll just mention for later that that combination is what can shift omega matter around, because these parameters are all correlated. So the fact that we see a slightly lower omega matter with our new, what we call P-ACT combination, is actually connected to measuring the damping tail better. Okay, so that's one of its roles. That's one of its roles. Then we all love to combine and test consistency, right, between the CMB and late time data. So as we gather more from Roman, from Rubin, from Euclid, I'm sure we'll be doing this more and more. And this is just an example of how you can take the model that primary CMB wants, and you can compare it against the measurement of, for example, the CMB lensing power spectrum, where it's looking very consistent with the data. And as well with the DESI DR1 and here DR2 data, these are the measurements of the distances from DESI as a function of redshift. And the prediction of the CMB preferred model is shown here. And actually, when we use our sort of P-ACT combination, the consistency with DESI DR2 is a little better, 13% PTE, no problem, compared to the Planck alone model. This is, again, I'm sure a role we'll continue to see happening with the SO data compared to Euclid and Rubin and Roman in terms of cosmology. I'll go past this and come back to this. Okay, so one of the roles is to be an ever better primary CMB measurement, and again, SO will improve those that E-mode spectrum that's got tiny errors. The errors will get tinier, and we'll get better constraints. But the other role is to be a backlight, and to be the secondary, to use the secondary signals of the CMB as a direct probe of mass and gas through gravitational lensing and through the Synergies effects. So you can use that to test the growth rate of structure, in particular in combination with optical surveys. This is now our 2-year-old image that you may have seen, which is imprinted on a backlight of where the dust in the galaxy is. This is an image of our CMB lensing map from ACT, where you're really measuring with high signals noise. Yellow points say there's more mass there. Purple say that there's less mass integrated there. You're really getting a measurement of the mass distribution integrated along the line of sight. This signal, the sort of power spectrum of this signal, had a signal-to-noise ratio of 40 or so. SO will go up to more than 100 and will give us percent-level constraints on sigma 8 of Z. And in particular, will just be really exciting for cross-correlating with Roman, with Rubin, with Euclid. And again, we'll fill in these gaps down here with SO. We can also then find galaxy clusters. I pointed out some of those already. We're finding roughly 10,000 right now with ACT that have redshift information that you then get from the optical surveys. There's great synergy there. And you can also try and do mass calibration from the optical surveys too. here's the number density as a function of redshift of the clusters that we have already. There's 10,000. This should go up to about more than 30,000 with SO. And currently, it's looking at masses that go down to like 2×10⁻14 solar masses and out to a redshift of 2 or so. The blue points are our latest ACT sample. Now, what you can also do is not just look for the clusters, you can actually make a map of the gas pressure by combining your wavelengths together to produce a map of the gas pressure through the Observatory effect. Rather than just looking at points, you can actually make a map of it. And that's what this image shows here, where you see the bright points, you're seeing excess gas pressure. And this map is relatively noisy from ACT. But again, we'll just go down and we'll increase in sensitivity with the Simons Observatory. And you can do neat things like this image over here from Martin Locken, combines ACT and DES data, where you're looking for the cosmic superstructures, where she's stacked on dark energy survey data and aligned the stack to basically look for the gas aligned with cosmic superstructures out to quite high distances. And we heard yesterday about more work that's being done on these topics. And the last piece of cross-correlation work is mapping the baryon profiles. So you can use the kinetics in the Observatory effect, which basically traces the motion of baryons in the universe. It imparts a kind of Doppler effect on the CMB. If electrons are moving, the CMB scatters off it, and depending on whether they're moving towards or away from you, it gives a little Doppler shift, and you can see it. But you really need to find it by stacking on places that you know to look, and that's where you use the optical surveys. And so far, DESI has been, and others have been used to do this. And this figure shows our latest result from ACT and DESI, with about a 10 sigma significant detection of this stacked KSC signal as a function of distance from the galaxy group in DESI. And this curve tells you the profile of the gas as a function of distance from the center of the galaxy group. Again, I haven't got time to go into this. There are lots of experts in this room who may be talking about this more, and you can certainly talk to them about it. But again, this is the statistic that will go up fastest in significance. Right now, it's sort of 10-ish sigma. It's going to go up to 100 sigma or more if you combine SO with Rubin. And I don't have the forecast with Roman, but we should for sure do that. OK, let me tell you about the status. So those are the to recap, right? The CMB has a role as a primary CMB observer and as a secondary CMB provider of late-time observations of mass and gas. Let me now just review where we are with these surveys. The ACT status is that the final big data release, DR6, is out. All of the maps that we've been working with and doing science with, they're all public. They're on NERSC and they're on Lambda. And we also have provided some notebooks for people to use with them. So if you want to cross-correlate anything with our CMB lensing or our Compton Y maps or do anything like that, it is all available, and we are eager to help people do that. On the SO status, I'm really excited because we are now commissioning that large aperture telescope. And that's only been in the last few months. That's new. And I said over there, the SATs are these small aperture telescopes that are looking for the gravitational wave signal. We have also those operating. What I'm showing you here is the very first light image we took of Mars in February. When you calibrate a CMB experiment, you look at a planet. And so that's what you do to figure out its beam, to figure out what's going on. That's what you do. And so this is Mars. And then a little later, over the course of the last months, this is a first snapshot of a map of the CMB made with just 10 hours of data. It looks a bit ratty around the side because that's just noise. You sort of cross many observations together, and so the highest quality will be in the middle. And even just taking those 10 hours of data and cross-correlating that map with the previous one we'd made from ACT and Planck, you can measure the power spectrum. These are the acoustic peaks in the temperature power spectrum. they're not perfectly aligned with the theory because it's not even calibrated yet. But this is just 10 hours of data in a frequency channel. So we're really excited about this. And then this is just 20 minutes of data taken on the galactic center with our multi-wavelength data. And you can already see, the Sag A star and Sag B2 in the kind of more synchrotron and dust parts of the emission. So one thing that I haven't really got time to say, but I was inspired by hearing the earlier talk from Judy, is that another big part of SO that we're very excited about is our time domain work, which we've never done before in this field properly. And now we're devoted to doing millimeter transient work. So I didn't put that in, but it is something that we are building pipelines to do actively. So, okay, just finally, timeline. We were on the sky with ACT for 15 years, running kind of this through 2007 to 2022. We're now on the sky with SO, and the plan is to run it for almost a decade, if we can. And so if you want to think about what data is going to be there during Roman, during Rubin, Euclid, the data that exists now to start doing your science with is ACT. But very soon, and we're really committed to getting the data public, it'll switch to being the SO sky that will just get deeper and deeper as we integrate. And we're, again, very committed to public data releases and working with you all. So just to conclude, ACT is done, the data are out, and we're starting to commission this beautiful new observatory, giving us both a view of the early universe and a new view of the late time universe too. Thanks.
Thank you. Question here?
Probably naive question. Any plans for the primary or B modes?
That's what these are for. Yeah, absolutely. So these three telescopes, hidden, you can't see them. They're hidden inside ground screens because they try to shield them from emission from the mountains. They are half-meter telescopes that are exactly designed with this for the B modes. And they're on the sky already. We've started to take, I haven't showed it here, we've got early maps from those. And those together are targeting, a sigma R of about 0.002 to 0.003, just for people who carry this number in their heads. It's about four to six times higher than the kind of like than the community's sort of ultimate goals for example, S4 had been. And we've got 3 more coming. So the UK are building 2 more. I can't exactly remember where they are on the site. There's 2 more of those from the UK and 1 from Japan. So we'll have 6 in the next few years. And then the site is ready to take more. So, yeah.
Question in the back?
With the unfortunate news about CMBS-4, are there planned extensions for science or upgrades that are in the works?
Excellent question. Okay, so there's the upgrades that are already in the works. Let me review what those are. So already in the works, so this big telescope has got this giant camera in it that currently is only half full of detectors. And those are and the other half is what the NSF is supporting us to fill and should be on sky in the next, by 2028. So that's already funded by the NSF and in the works. And then the 3 additions to these small telescopes are also funded by the UK and Japanese institutions and are in the works. So that will be that's our already supported expansion. But as I said, you can do more. And so we've, as people may have seen, right, the news that S4 has been cancelled, but that the agencies still want to support this science. There's a clear path to doing more at this site, and things. I'm sure discussions will happen. It's still early days.
All right. So one question here, then here, and then we'll call it. All right. Nico?
The previous slide where you showed the center, the galactic center.
Yeah.
So the map, is it like the zoomed in one, the CMB?
Sorry, it's a different map completely. So is that if that's these are two different maps.
Okay.
This is a little bit of the sky in what we call Bus North, so it's it's very far from the galactic center, and this is a dedicated measurement of the galactic center.
Why does it have these like more dense in some of the parts?
Here.
No, in the.
Here, this is still just this is noise. So it's such a small amount of data, and you observe the sky by doing this basically. And as the sky rotates, you do this. The sky, you do a thing called cross-linking, right, where you see things in multiple directions, and your noise gets better. And until you've done that, the edges of a map are noisy. So this is it's just early days. It's such little data. Yeah.
Yeah, it's really cool that you can see the galaxies using ActMap. Are those from direct emission or is it?
It's basically the orange spots are jets from AGN. So we're seeing synchrotron emission from jets coming at us. Sorry.
And the blue like.
Oh yeah, it's dust. It's dusty. Yeah, it's dusty. They're dusty nearby dusty galaxies.
And how many galaxies do you see?
Okay, so I have this didn't have this on the slide. So altogether, we detect about 20 to 30,000 galaxies, but they're mostly AGN. So the number of dusty galaxies is lower, and especially the resolved ones is lower. I don't have the number off the top of my head. Fewer, yeah.
All right, we'll hold any further questions for the coffee break. Thank you very much. Next we have Rio Terasawa telling us about insights from HSC Y3 Cosmic Share and prospects for HSC final year analysis and stage 4 surveys.
Too long?
Sorry?
Too long?
It's fine. Is there a green light?
Yes.
Great. And here you go.
Oh, no, please. I have here.
Right.
Someone's sharing.
If someone online is sharing, we've got one more in-person talk. Let me fix that.
Okay.
There
Okay. So, I'm Ryo Terasawa. I'm a final year PhD student working at the Hubble IPMU. So today I'll talk about joint analysis of CMB lensing, CMB and cosmic shear from HSC 3. So as Joe gave a great introduction for CMB and CMB lensing, with combining this with cosmic shear, we can probe a great wide range of the scale and also wide range of the redshift using those combinations. And let's see, let me more talk about this cosmic shear part. So for cosmic shear or weak lensing, I use HSC 3 data, which covers 400 square degree sky, and HSC have deep imaging that results in the very high number density of source galaxies, which is among the most dense sample in the stage 3 surveys, and it's most close to stage 4 surveys, for example, like Rubin and Roman. So what I'm talking about today is going to be applicable for those stage 4 survey. So back to this slide. So one thing we can do with this combination of probes is tracing or testing the shape of primordial parseton. So because those structures, the seed is from the initial fluctuation in the inflation, all of these CMB lensing, cosmic shear, probes these primordial fluctuations. And especially in terms of scale, those CMB mostly probes large scales, while cosmic shear can probe a smaller scale. So in that sense, those two are complementary to each other. So let me demonstrate how this cosmic shear can be used as a probe of this primordial power spectrum. So here on the left, I'm showing the primordial power spectrum. And in the black line, I'm showing the standard single power model. And in the colored lines, I'm showing some parametric model of the primordial power spectrum, including the spectral index running in the red. And on the right, I'm showing the two-point correlation function. And again, this black lines is correspond to the single power primordial power spectrum. And the colored lines corresponds to modified primordial power spectrum. And we use these white regions for the data analysis. And as you can see, these white regions we probing is, for this scale, we can see the difference from the changing primordial power spectrum. And to model this nonlinear power spectrum that goes into weak ranging prediction with the modified primordial power spectrum, we use a halo model. And we change the input linear power spectrum according to this change in the primordial power spectrum. And here's a constraint on the primordial power spectrum. So first, let us see the it's busy plot, but let's see blue shaded regions, which is a constraint of 1 sigma, 2 sigma, 3 sigma, with combined data of CMB and CMB ranging and the BAO. So without cosmic shear data, those CMB can constrain primordial power spectrum roughly down to K of 0.2-ish very tightly. And when adding this cosmic shear data, we can greatly improve the constraint that became this now red shaded region. So cosmic shear has can be used as this probing small scale primordial spectrum. And what we found is those primordial power spectrum is consistent with a standard power law model down to very small scale. And this primordial power shape tells us basically the shape of the inflation potential. So that gives us a great implication for inflation model. So that's one thing we can do, this combination of the CMB ranging and cosmic shear. And another thing we can do is tracking growth history throughout the universe from recombination to the very present day. So here, in the particular plot, I'm considering the growth separation, the SA tension in mind. So if we are supposed to solve or mitigate this SA tension in terms of the redshift dependent way or that solution, we need to suppress the growth in the late time. And to achieve this, we rescale the linear power spectrum parameterized as this with two parameter beta and p. So here beta controls the overall suppression at the later universe, and this p controls when this suppression starts. And also this parameterization matters only after this dark energy density starts to dominate. So this suppression is actually similar to that of the varying growth index, but this has slightly more flexibility due to this one more parameter. And this modification is to the linear power spectrum level, but for the nonlinear power spectrum, we again input this modification of linear power spectrum into the halo model, HM code, and to model the cosmic shear. So here on the left panel, I'm showing the difference due to this suppression model in orange. So even in the nonlinear level, it almost shows no scale dependence. And on the right, I'm showing the effect on the cosmic shear. So as you can see, orange line corresponds to this suppression model, which shows redshift dependent, but almost no scale dependent. So that's model we consider here. And here's the results of the joint analysis, again, of the CMB lensing, and the cosmic shear. And let's focus on this suppression parameter beta. So as you can see, we have found around 2 sigma hint for positive beta. That means 2 sigma hint for growth suppression at the late time. And comparing this different number of p, which correspond to when this suppression happens, we found a larger one is favored. That means more of rapid suppression starts at the redshift 0.7 each is favored in this particular combination. And we can compare our result with other CMB ranging cross correlation with, let's say, galaxy cluster. So here on the left, I'm showing our constraints assuming this suppression model with rapid one in orange. I'm showing sigma 8 as function of redshift. So as you can see, that shows a suppression towards a lower redshift like this compared to the usual lambda CDM. And we can compare this with CMB ranging cross galaxy clustering. Here I'm showing the DESI LRG cross CMB ranging. And they also show growth suppression compared to the Planck. And if we focus on the this individual fit for each redshift, that happens to show a similar like trend towards a low redshift. And this suppression might be related with the recent DESI found dark energy model. That would be also interesting. So let me conclude here. So, I talked about a joint analysis of primary CMB ranging, and cosmic shear. I talked about HSG, but I believe this can be used for Roman and future data. And this combination can cover a wide range of scales, and adding cosmic shear can improve constraints on primordial path spectrum at small scales very well. And also with this combination, we can cover entire growth history basically. And we found 2 sigma hint for the growth suppression that happened in the late time. And I only talked about actually joint analysis, not cross correlation, but as we see in the Joe's talk, there are many overlap between future CMB lensing and Roman Rubin. So we can definitely do cross correlation between these probes. Okay, let me stop here. Thank you very much.
Great, thank you so much. We have time for 1 or 2 quick questions.
Yeah, at the start you were talking about the primordial power spectrum tests. Did you translate that into constraint of the spectral index? And
I also did such thing like here, just spectral index learning. So in terms of learning parameter, yeah, we constraint. So overall, we found nothing beyond the standard Parallel model. But I'm sure we can constraint with this combination, yes.
Great, thank you very much.
Thank you.
next we have, the next two talks are virtual. So first we'll be hearing from Ma Perez-Sarr, who's going to be talking to us about a window into gravity, cosmic voids across CMB lensing. So Ma, feel free to take over the screen share. We can't hear you. Can you try talking again? Sorry, we appear to be having. Yeah. Yeah.
It's hard to keep talking.
Yeah, try and keep talking and see. We're having some AV issues, sorry.
Hey, Mark, can you share your screen again, please? Okay, we cannot hear you.
Do you think that's on Ma's end or ours? We can swap the order of the speakers if you.
Yeah, Mar, I'm not hearing you online either or in the room. Can you check your microphone settings?
Can someone else online please try speaking? Ismail, since you're going next, could you please try and speak and see if it's an issue, if you're able to?
Yes, hello, can you hear me?
Yes, we can. So what I think we'll do is swap the order of the talks. So Ismail, if you can, if you're happy to do your talk first, if you could screen share and move on to that, and then possibly we can restart the computer and check the microphone settings in the meantime. Great.
Okay,
So instead we'll be hearing from Ismail Torino about the Euclid mission computing the survey. So
okay,
Ismail, please feel free to share screen.
Okay. Right. I'm sharing. Is it?
Yes, we can see your screen. Feel free to get started.
Okay. Right. So let me just. Okay. Hello. So, well, apologize for not being there in and having to present remotely. But well, so I'm Ismael Tereno from the University of Lisbon in Portugal. I'm currently the Euclid Consortium survey scientist. And so this talk will be about showing a bit the implementation of the Euclid survey. I also served in the definition committee of Roman's high latitude wide area survey. So I'll try to make also some connections with between Euclid and Roman. So, right. So now, so Euclid is in space for 2 years now. July 2023 was the launch. And it has several components, in fact. So there's the wide survey that we aim to reach 14,000 square degrees. We already heard that it will be difficult to achieve that during the nominal mission. There's also the deep survey, in which are 53 square degrees spread in 3 fields. And there's more than this. There are also some additional fields, some auxiliary fields like Cosmos or Chandra Deep Field South that are observed also with similar depth than the deep survey. There are some observations already that can end up being part of a medium deep survey, so with the magnitude depth between the wide and the deep. There's also a very extensive calibration program. There's still some free time that could be used in additional programs, and that's still not decided yet. There are observations, like Julie mentioned this today, about there was a galactic bulge survey already observed. So this was motivated by interaction with Roman to have some data already in advance for the time variations. And also very important, the ground-based observations. So there are the unions, so a joint effort of several telescopes in the Northern Hemisphere, and also it's covered by the Dark Energy Survey, part of the footprint of Euclid. And so this is very important because we have a wide filter, a broad filter in the optical, like it was mentioned already, and then there are the three filters in the near infrared and the grisms. So I give here just some features of Euclid. There's also, so I also want to mention the reference observing sequence, which is made so each time that there is we make a pointing for the wide survey and also for the deep, there is we take 4 exposures with this Dieter pattern, and also the grism wheel is rotating between the exposures to have different directions for the spectra. So all this is done in each pointing. That takes around 70 minutes. So we are able to observe 20 fields of the wide survey per day. Now I put here this table showing some features of the 2 surveys. So I mean the surveys of Euclid and the surveys of the high latitude wide area survey of Roman. So the wide area survey of Roman is the core survey is the medium, so-called medium tier, which is done. So this is according to the recommendations of the definition committee that then were passed to the ROTAC. And so this is in according with the final report of ROTAC. So it's the in-guide case. So the medium tier has 3 filters in the near infrared, like similar to the ones used in Euclid. And then there's the extended area of so-called wide tier that is done only in one of the filters. So we can see that the depth, it reaches fainter magnitudes, the Roman with respect to Euclid in the near infrared, but then Euclid has the optical part. We can see also that the deep survey of Euclid is designed to be 2 magnitudes deeper than the wide, while in Roman is 1 magnitude deeper, even though there's a small part inside the deep field that is 2 magnitude deeper. You can see also that the strategy is different. So while in Euclid we have these 4 exposures and everything is done at once, in the same visit, the exposures, the grism also. While in the strategy here in Roman, I believe it will be to have 2 visits. So there are 3 Dieters instead of 4, and then the pointings are revisited again at a later time. And also the spectra are maybe done in a different time as the imaging. So you can see also here the number of galaxies for weak lensing that are expected to be higher in Roman. And you can see also the time. So Roman is a much faster survey. So the medium tier is done in 370 days, while the Euclid wide survey takes so all this time you can see here. So that's this comparison table. So the science goals are also, the cosmology goals are also similar. Here I want to highlight that with this type of images and with the features of the instruments, even though it's built for cosmology, it can provide lots of non-cosmology science. So as a curiosity, I made this compilation of the first 200 papers of Euclid, looking at the sections in the archive. We can see that while in the preparatory paper, so before the first data releases, the vast majority were focused on cosmology. Then when we had the first quick data release, the actual science papers are, of course, focused on non-cosmology cases. So this also shows the importance of this type of surveys also. So now moving now to the survey implementation part. So just here, just to show you. So this is done in different steps. We have here on the left the Euclid Consortium part. So the Euclid Consortium survey group is the one that has defined, especially during the preparatory phases, several optimization criteria to guide the implementation. Things like recommending location for the deep fields, fine-tuning the region of interest, besides the one that came from the baseline, computing sky background. And then the SOST, which is a survey operation support team, is the group that actually implements. So it's also a group from the Euclid Consortium. So this work is not done directly at ESA. And so we do the mission planning, so the schedule of the 6 years of the mission, so the full schedule of the pointings. And this is done with the software purposely developed for this. And then we deliver this to SOC. And then, so this is done with all the inputs from optimization, from the calibration requirements and all the system requirements. And then SOC then validates and translates to really the pointing commands. And now we are more in a feedback loop, which we have additional feedback from the operations, from the science performance, from data processing, to replan, to reschedule, to see what was missed, what can be improved. So what is our work then? So we start by, so the main very important ingredient are the solar angles. So you can see here a model of Euclid. And so basically, if we think that we are in ecliptic coordinates, for example, here this diagram on the upper right side, we see the visibility areas. If we are at a certain location in the orbit, so this meridian marked in blue, this blue line, the pink area is the visibility window, according to the solar angle restrictions. So we can observe so this is the general picture that will be changed then, but in principle, we can observe on a transit meridian, and we could tilt a bit towards the sun or away from the sun, and we can also, which is the solar aspect angle, and we can also roll around the telescope axis. And with this, we can see here in this animation, I'm not sure if you see the animation, but so we can see the bands as the Euclid moves in the orbit. We have these two lines that mark the visibility windows. So it's this that we can see also on the right. So the first thing we do is to observe all targets, so the deep fields and the calibration targets, such that according to the sequence, according to the cadences that are required, and that's you can see here in the lower left side in different colors. So this is a chronogram. Each line is 1 year of observations, and in each line there are it's marked with different colors, the different target observations that are summarized in this table, and this already takes 25% of the total time. So now in between these colors, we have now the free time for the available time to schedule the wide survey. So now an important point is that this is done with the tessellation, which means we have the tessellation on the sky with fixed tiles, and then each pointing will be constrained by the position angle of the tile. So this means that we can no longer observe, for example, in the polar areas that were perennial visibility. Now it's no longer the case because we need to observe with a certain orientation. So we can only observe in a limited amount of time during the orbit. So this reduces strongly the visibility window that you can see here in the second panel. And then there was this problem that Xavier mentioned, that the stray light from the sun entering from certain paths, and this forces to rotate. So the Euclid now needs to operate with a rotation of this alpha angle. And because of that, the visibility window dramatically decreased to this third panel here. So this means it would be, at first sight, it would be impossible to schedule the survey given these all the constraints. So now the solution we found was to relax the constraint on the tessellation. So now we have a tessellation that each field of view can be placed with 3 degrees variation according to the natural orientation of the tessellation. So it means that now we can reach a little more in longitude when we are in a certain point in the orbit. We are not so strongly constrained as in the other case. But because of that, each tile now is not perfectly aligned with the neighbors, and then we'll have some overlap. So in total, this increases the global overlap to 14%, while before it was only 4%. This is why we are not reaching the 14,000 square degrees. So now here you see on the left side, bottom left, the schedule made already. So the parts that were white before now are pink, which means they are filled with a patch of the white survey. And here you can see the breakdown of all the usage of the time. So about 2/3 is used by the white survey. Then there's the deep survey and so on. And there are still 5% of the time that is not allocated yet. We'll see next why is that, but can be used perhaps for general other observations. And there's already 5% of the time that was lost or skipped to do the decontamination or some failed observations that needs to be rescheduled. So now, just to show you then how does it look in the map. So you can see here, these are different patches. So we have the ecliptic plane and the galactic plane in white that are not the parts that will not be observed by Euclid. And the other parts that are colored in blue or also in green, in principle, could be observed, but there's no time to observe everything. So the ones that are observed, that are scheduled, are the ones in colors from dark blue to pale blue. So you can see we move from the polar regions to the ecliptic plane, from the best, from the lower zodiacal lights. And then these are the patches that we'll build one by one. In each survey window, we define a patch. And then inside the patch, there's a second part, let's say a smaller scale problem, which is, so there's a large scale puzzle to fill all these patches, and then there to place the patches, and then the small scale puzzle to fill the sequence of tiles within a patch. That's what I show here in the lower right side. And as you can see, it's a problem because the patches move toward the poles, they narrow down, so we cannot just go up and down along a meridian, but need to cross paths, to jump on bright stars. So this is the core of the algorithm, in fact. I also mark here the deep fields with crosses. And finally, I overlap here the Roman footprint. So the wide area survey footprint. So you can see the medium tier and the wide tier in red and green. You can see that the medium tier is very much overlapping the Euclid footprint, 91% overlap, while the extension of the wide goes towards the ecliptic plane and it's outside the region of interest of Euclid, so it has a very low overlap. And this is it, the end of my talk. So here it's just a small part, a very small part of the file that we deliver to SOC with the list of pointings. Thank you.
Great, thank you very much. We are running over time, so I'm going to ask if people have questions, please post it in the Slack channel so that our virtual participants can respond to them and so that everyone can see the answers. And we will move on to Mark, who will be telling us about cosmic voids cross CMB lensing. Let's just check that the DV is working.
Can you hear me now?
Yes, we can hear you now.
Ah, fantastic.
We can hear you.
Great.
Just go ahead and share your screen.
I will share it now. Can you see my screen?
Yes, we can see it.
Okay. Okay. So hi everyone. Sorry for the mess, and thank you for giving me here the space to talk today. To talk today about my project. I'm Mar Perez Sar. I'm a third-year PhD student in the Canary Islands, working with Carlos Hernández Monteagudo and András Kovacs. And today I want you to introduce this project, some forecasts that I did for the Roman telescope regarding Roman voids cross-correlated with CMB lensing. As I mentioned, I did this together with my two supervisors, but all this project started at the Flatiron Institute with Alice Pisani, which was really an amazing experience. So before jumping to the results, I want to give you a little bit of context of this project, of the motivation of this project, by answering these three simple questions: what I want to observe, why are we interested in this, and how I do science with it. So what I want to measure, as I said, is the cross-correlation of voids with CMB lensing. And voids are these underdense regions in the large-scale structure that occupy the vast majority of space in the universe. And of course, they are biased tracers because we find them because of the galaxies, and they retain the 3D map properties of the large-scale structure. On the other hand, we have the CMB lensing that tells us about how CMB photons are deviated when crossing through all the large-scale structure. And we can quantify this deviation by different quantities, but here we are going to focus on the convergence, that we can imagine that if we have like a circular patch of photons, the convergence will give you a slightly smaller area of the circular patch, and a divergence will give you something bigger. The divergence will be caused by massive structures, while the convergence, that is a negative signature, will be caused by cosmic voids. Why are we interested in this? Is first to know the Roman scope abilities, but also because along these years there were some tensions in the literature regarding CMB lensing measurements and also integrated sub-Wolf effects that they prove different dependencies of the gravitational potential. So with this work, we also wanted to assess how the impact of mock catalogs look like in the lensing signature and so on. Finally, once we have data, we want to extract cosmological information, but here we just do the forecast. So how we do science with this, because we lack of analytical models for this quantity, we need to go from simulations to real data. And here we have an extra challenge, and is that the mock catalogs that are in the literature most of the times doesn't have CMB lensing companions because it's expensive to do. So what we have to do here is to take mock catalog, in this case for Roman, from the literature, and replicate it in a simulation with CMB maps. In this case, I'm using the Roman as a reference catalog. I'm using the one of Zai et al. Of 2021. And for my simulation with CMB maps, I'm using the Agora simulation of Yu Kiyomori. The way that I'm painting galaxies into halos is with the subhalo abundance matching method, which simply I choose the closest neighbors in my simulations that replicate reference catalog without any repetitions. Here you can see a little bit the processing. So there is a first step before the subabundance halo matching model, and is that I subsample a little bit the density of the Agora files that are halos basically to the Roman raw density, because in the Roman reference catalog there are two versions. One is like a lot of galaxies, and another that you can apply a flash cut to observe what Roman will see, sorry. And so as a first step, I subsample to the Roman raw density and taking 4 methods. So by mass or randomly, and considering all or ELG type galaxies. With this, I have input files with different bias biased that I can plug in my sham. Then in the sham, I also use 4 different methods. One is not properly a sham because it's just subsample, randomly subsampled points. So I just want to replicate the same D and D set. But then I include all other parameters, for example, halo mass and environment, etc. So I have this method to create different mock catalogs of different levels of complexity, and they have a slightly different bias. Then I find the voids, both in 3D and 2D. Those are the, in 3D void finder, I'm using Revolver, which is a void finder that uses geometrical information. And as a 2D void finder, I'm using the one of Sanchez et al. That just projects the density in density maps and found the other densities there. And finally, I measure the signal. First, I apply a little bit of smoothing in the CMB map, and then I stack the signal. I cut patches of CMB lensing signal in the void positions, rescale them, and sum them to have bigger signal to noise. For the uncertainties, I do the same thing, but instead of the CMB lensing map, I replace it for random realizations to test the null hypothesis. So the results. I'm going to show you like 3 bullet points of results. First, how these different mock catalogs that I've explained you affect void statistics. Here, what you can see is in each column, you have 2D voids and 3D voids. And in every panel, you can see the different sham method, and as every color, the input file. Remember, the input file has some differences in the bias, and then we have these different methods. So this is the number of voids, and you can see, for example, that in the case of having only, of taking into account only the same number of objects, but without any other criteria, I have very different number of voids in 3D because of this bias. And this also translates to the, for example, for the sizes of the voids or for the minimum density. So with this, we can see firstly that the method that takes into account the mass and some parameter regarding the type of galaxy, that is what I'm taking is actually the specific star formation rate, gives me the better results. For the 2-point statistics, I do the same, and the conclusions is the same. Like I have different variations regarding the biases, but the methods that best work for me are the one with the mass and the type of galaxy. And also, if I cross-correlate galaxies with voids. Here I show the monopole for the 2D voids, and 3D voids, also the monopole and the quadrupole. So the main ideas that I want you to take from here is that void and galaxy statistics, as we expected, are significantly affected by these different mock catalogs. The ones with halo mass and halo mass combined with galaxy type parameters provide me a better match, and 3D void statistics exhibit greater deviations. Second, exactly the same thing, but how different mock catalogs affect lensing signal. So the lensing signal, I said, is a convergence. So you have a negative signal in the center of the void that you can see here as the profile. Then you have kind of a compensation wall, and then go to the mean. So if we plug in all the mock catalogs that I've been explaining to you, we see something pretty surprising, at least for me, and is that no matter which mock catalog, they look exactly the same. So there are small differences, but here we are not considering an instrumental noise. So even if not considering instrumental noise, the differences are really small. And we think that this may be due because the lensing, the CMB lensing tracks the underlying dark matter density. So it's not as biased as the other statistics. This is for all type of voids, but voids can come in different flavors. Here I have different void types for 2D in the upper panel and for 3D. And even if I consider different void types, I have the same result for all the mock catalogs. So here what I display is the kappa, the signal in the very center of the void, in the maximum, I mean in the compensation wall, and also a difference of the external part of the void and the internal part of the void. And by comparing all these cases, I obtain the same. If now I compute the signal to noise, then I have some some dispersion, and this comes because first of all, we have cases with more number of voids, as we have seen in the first bullet point. But also, if we divide by the number of voids to get rid of this thing, we can see also that there are some voids that are more prone to give you a pristine signal than others, and this has to do with the bias. So in this part, we have learned that the voids cross CMB lensing signal remains stable across different mock galaxy catalogs and is less affected by bias compared to other galaxy-based statistics. And this robustness is really interesting because it makes it a reliable cosmological proof and suggests that catalog construction is unlikely to be the main cause of tensions with real data. So if you have a tension in your data when comparing simulations to observations, it might be that you're not assuming the same cosmology or something else regarding systematics and so on, but it's less likely to be because of the mock. And in the very last point, sorry, if we take the best case, the one that gives me the lowest RMS in comparison with the reference catalog, I do the forecast for 2D voids and 3D voids, taking into account two things. First, different smoothings in the CMB map, which is in the x-axis, and then different instrumental noise. So the upper panel will be the raw signal, and then the signal with instrumental noises for CMB stage 4 instruments, Simon's Observatory, and Planck. And what I can see here is, of course, Planck is more noise dominated. So with Simon's Observatory and CMB stage 4 instruments survey, we are going to enhance the signal to noise, but also that the smoothing can erase some of the instrumental noise and can help us to maximize the signal to noise. So for example, Planck will, with a smoothing of 1 degree, can have the highest signal to noise, but for example, for Simon's Observatory, 0.5 will be enough, and for stage 4 survey will be 0.2. So from this last part, I've learned that upcoming experiments will greatly enhance the signal to noise. I also show here some of the signal to noise projections, and something interesting is that the smoothing depends on the survey and the void finder, but it really helps us to maximize this signal to noise. And Roman will be great to prove this observable in higher redshifts, but larger footprints will, of course, further improve the cosmological potential. And I will leave you with take-home ideas. Thank you.
Great, thank you very much. Because we are running a bit late, again, we're going to ask that questions be posted on the Slack channel and that they be posted publicly so that everyone can see the questions and answers. So we're going to run the morning break until 11:45, so it's 5 minutes later than on the schedule. One thing to remember is that in the next session, right before the end, we will have the group photo. Another thing is to sign up for the dinners tonight. And finally, I'll remind people for the that are presenting in the next session to please come up and do their speaker check. But go ahead and grab your coffee and we'll see you back here at 11:45.